6.2 Changing the conditions of an equilibrium reaction. Some industrial processes, like the production of ammonia or sulfuric acid, have reversible reactions as a key step. In closed systems, these reactions would produce equilibrium mixtures containing both product and reactants. In principle, you would like to increase the proportion of products. For this reason, it is important to understand how to control equilibrium reactions. It is possible to change the proportion of reactants to product in an equilibrium mixture. In this way, you are able to obtain a greater yield of the product. This is called changing the position of an equilibrium. If the proportion of products in an equilibrium mixture is increased, the equilibrium is moved to the right, or in the forward direction. If the proportion of reactants in the equilibrium mixture is increased, the equilibrium is moved to the left, or in the backward direction. You can often move the equilibrium position to the left or right by varying conditions like temperature, the concentration of species involved, or the pressure, in the case of reactions involving gases. Le Chatelier's principle is useful because it gives a rule. It tells us whether the equilibrium moves to the right or the left when the conditions of an equilibrium mixture are changed. It states, if a system at equilibrium is disturbed, the equilibrium moves in the direction that tends to reduce the disturbance. So, in other words, if any factor is changed which affects the equilibrium mixture, the position of equilibrium will shift so as to oppose the change. Le Chatelier's principle does not tell us how far the equilibrium moves, so we cannot predict the quantities involved. If you increase the concentration of one of your reactants, Le Chatelier's principle says that the equilibrium will shift in the direction that tends to reduce the concentration of the reactant. Look at the reaction. B plus A is equal to, but can be converted back to, C plus D. Suppose you add some extra A. This would increase the concentration of A. The only way these systems can reduce the concentration of A is by some of A reacting with B, so forming C and D. So adding more A uses up more B, produces more C and D, and moves the equilibrium to the right. You end up with a greater proportion of products in the reaction mixture than before you added A. The same thing would happen if you added more B. You could also remove C as it is formed. The equilibrium would move to the right to produce more C and D, using up A and B. The same thing would happen if you removed D as soon as it formed. Pressure changes only affect reactions involving gases. Changing the overall pressure will only change the position of equilibrium of a gaseous reaction if there are a different number of molecules on either side of the reaction. An example of such reaction is N2O4, which is dinitrogen tetraoxide, is equal to, and can be converted to, 2NO2, which is nitrogen dioxide. Increasing the pressure of a gas means that there are more molecules of it in a given volume. It is equivalent to increasing the concentration of a solution. If you increase the pressure of this system, Le Chatelier's principle tells us that the position of equilibrium will move to decrease the pressure. This means that it will move to the left because fewer molecules exert less pressure. In the same way, if you decrease the pressure, the equilibrium will move to the right. Molecules of N2O4 will decompose to form molecules of NO2, therefore increasing the pressure. Dinitrogen tetroxide is a colourless gas and nitrogen dioxide is brown. You can investigate this in the laboratory by setting up the equilibrium mixture in a syringe. If you decrease the pressure by pulling out the syringe barrel, you can watch as the equilibrium moves to the right because of the colour of the mixture. Because the colour of the mixture gets browner. Note that if there is the same number of moles of gases on both sides of the equation, then pressure has no effect on the equilibrium. For example, H2 plus I2 equals, but can be converted back from 2HI. In both cases, you get 2 moles. The equilibrium position will not change in this reaction when the pressure is changed, so the proportions of the 3 gases will stay the same. Reversible reactions that are exothermic, give out heat, in one direction are endothermic, take in heat, in the other direction. See topic 4.4. The size of the enthalpy is the same in both directions, but sign changes. So, suppose you increase the temperature of an equilibrium mixture that is exothermic in the forward direction. An example is 2SO2 plus O2 is equal to, and can be converted back from, 2SO3. The enthalpy change of this reaction is equal to minus 197 kilojoules per mole. The negative sign of the delta H means that heat is given out when sulfur dioxide and oxygen react to form sulfur trioxide in the forward direction. This means that heat is absorbed and the reaction goes in the reverse direction, that is, to the left. Le Chatelier's principle tells us that if you increase the temperature, the equilibrium moves in the direction that cools the system down. To do this, it will move in the direction which absorbs heat, is endothermic, that is, to the left. The equilibrium mixture will then contain a greater proportion of sulfur dioxide and oxygen than before. In the same way, if we cool the mixture, the equilibrium will move to the right and increase the proportion of sulfur trioxide. The effect of temperature on the dinitrogen tetroxide nitrogen dioxide equilibrium can also be investigated using the same apparatus used to investigate the effect of pressure on this reaction. The reaction is endothermic as it proceeds from dinitrogen tetroxide to nitrogen dioxide, the forward reaction. You have N2O4, which is equal to, and can be converted back from, 2NO2. The delta H of this reaction being plus 58 kilojoules per mole. The gas mixture is contained in a syringe as before. The syringe is then immersed in warm water along with another syringe containing the same volume of air for comparison. The plunger of the syringe containing air will rise as the air expands. The plunger of the syringe containing the N2O4-NO2 mixture will also rise, but by a greater amount. This indicates that more molecules of gas have been formed in this syringe. This is because the equilibrium has moved to the right. Each molecule of N2O4 that disappears produces 2 molecules of NO2. This is consistent with Le Chatelier's principle. When the mixture is warmed up, the equilibrium moves in the endothermic direction. That is, it absorbs heat, which tends to cool the mixture down. You should be able to predict the color change that you would see during this experiment, and also what would happen if the experiment were repeated in ice water. And finally, catalysts. Catalysts have no effect on the position of equilibrium, so they do not alter composition of the equilibrium mixture. They work by producing an alternative route for the reaction, which has the lower activation energy of the reaction. See topic 5.3. This affects the forward and back reactions equally. Although catalysts have no effect on the position of equilibrium, that is, the yield of the reaction, they do allow equilibrium to be reached more quickly and are therefore important in industry.